All right, hi everybody. So in today's lesson, we're going to talk about trig graphs and their inverses. To start, I want to go back and I want to review what it means to be an inverse. So let's just use a function here. F of x equals x squared. We've graphed plenty of parabolas. We've looked at that function multiple times. So if I just pick a value, let's say 2, if I plug it in, 2 squared becomes 4, means I have a point at 2 comma 4. Again, I plugged in 2. The function tells me the output is 4. So the inverse of a square is a square root. So that implies that if I put the y value, the output in here, it should be able to undo what happened in the last function and go back to the original value. Again, we've talked about, hey, inverses flip the ordered pairs. We go from putting in an x to get a y to putting in a y to get an x value. All right, so now we're going to apply that same idea to a trig graph. So if you look here at this first picture, all right, this first trig function here, this is the sine function, so this is just y equals sine of x. We know it's a function, it passes vertical line test, but if we look at the horizontal line test, which would tell me if the inverse is a function, it would fail horizontal line test, right? There's a horizontal line, it hits it more than once, fails horizontal line test. Right? I need to be able to find something that only has one x to one y. And that's called a one-to-one function. It just means that every x has one y and every y has one x. And so what I do is I look for part of this function that will actually pass horizontal line test. The key is that I have to include x equals 0, or I have to include a point that's right by the origin. So I'm going to highlight, I would start and include this part of the graph. I'd go from 0 up to pi over 2. But if I would start to come back down, that would immediately fail horizontal line test. So instead of continuing to the right, I'm actually going to back this up, and I'm going to get this entire piece from negative pi over 2 to pi over 2. And what that creates is a special part of that graph where, again, it still passes vertical line test because it always did, but this part will pass horizontal line test. So basically from the ordered pair down here, which would be at negative pi over 2 comma 1, negative 1, all the way up to here at pi over 2 positive 1. Again, that passes horizontal line test. So what this does is it kind of narrows down our graph. And so it narrows down our domain from all real numbers down to the values between negative pi over 2 and pi over 2. And the range is from negative 1 to 1. All right? So if I want to then graph the inverse of that, when I limit it to just that values and just those values where it's a 1 to 1, right, and it passes the horizontal line test, the inverse graph is going to be notated as y equals, and it's a capital letter S for sine, and that capital letter is what designates that it's that restricted part of the graph, right? So the point at 0, 0 would still be at 0, 0 if I did an inverse. Instead of going out to pi over 2 and up to 1, here we go out to 1 and up to pi over 2. This is the point 1 comma pi over 2. Likewise, I would go to have a point at negative 1, negative pi over 2. And what I could have done is graph these both on the same graph and understand, remember, in order to get this graph, I'm going to reflect it over the line y equals x. So the curve kind of bends the other way here. All right, and it creates that shape right there. That is the inverse sine graph, again, just for that restricted piece. The domain of this would be negative 1 to 1, and the range of this would be negative pi over 2 to pi over 2. So notice, again, the x's and y's just are inverted. Well, then you're asking yourself, Mr. Stringer, why is this important at all? Why are we talking about this? What does that graph do for us? Well, I focus on this range here, right? This range tells me I'm only going to look at values between negative pi over 2 and pi over 2. And the reason why you see that little unit circle over there is to relate it to that as well. We know pi over 2 is up here. We know negative pi over 2 is down here. We obviously know 0 is over here. So for the inverse, I'm only looking at the values between negative pi over 2 to pi over 2, which means I'm going to limit myself to looking at that part of the unit circle. And so here's how an inverse works in terms of trig functions. A regular trig graph, or a regular like unit circle question, I would say, hey, sine of, I'm just going to use pi over 4. Right? You can look at the unit circle, you'll know that's root 2 over 2. Right? Now, how the inverse works is now I'm going to give you capital S sine inverse. And now instead of giving you the angle and you telling me the ratio, we're going to just go backwards as well. All right? I'm going to give you root 2 over 2. You have to think what angle creates a sine value of root 2 over 2, and you would tell me pi over 4. So notice it is just the inverted way of doing this, right? Just like a square and a square root undo each other, a trig function and its inverse undo each other. So whereas up top in green, sine of pi over 4 is root 2 over 2, now I'm saying, hey, where does the sine value equal root 2 over 2? So I'm giving you the ratio now. You're telling me the spot on the circle in radians, right? And I can do this for a lot of different trig values. So I could do capital S sine inverse of like negative 1/2, right? If I only look between negative pi over 2 and pi over 2, the only spot that happens at is 11 pi over 6. But notice I'm going to call that negative pi over 6, so it fits the range and domain of these two graphs, right? And yes, that's going to matter, and yes, that's important. I want it to be one connected piece of domain and range, so it's one connected piece of the circle. That's why I'm not going to say 11 pi over 6, because that wouldn't be close enough on my graph. That'd be all the way, if you look at the original graph, that'd be all the way out here by pi over 2 pi. That's not really going to work. All right, so hopefully that kind of makes sense what we're looking at. So what I'm going to do is for each one of these, I'm just going to show you, hey, here's the part of the graph where we're going to look at that it's 1 to 1, all right, where every x has one y and every y has one x, all right? So like if you look at the next graph, all right, hey, this is, ooh, that's a highlighter, my apologies. This is y equals cosine of x. Again, hopefully you still remember all your trig graphs, all right? Here, if I started the origin and I started to highlight some stuff, I'll start at 0, 1. And as I go down here, this entire piece all the way to pi, right, that is one continuous piece, and it is passing vertical and horizontal lines. All right, so for this one, all right, my domain is going to be 0 to pi. That's the piece of the graph that has one x and one y connected to each other the entire time. All right, it passes horizontal and vertical line test. The range, much like the last one, is negative 1 to 1. And so when I go to graph the inverse of this will be y equals capital C cosine. All right, because again, it's telling you it's for that restricted piece. I'm going to have that point here at 0, 1. Now I have a point at 1, 0 on the inverse. This was pi over 2 comma 0. Now it's 0 pi over 2. And down here it's pi comma negative 1. So I need negative 1 pi, which will be right up there. And if I drew the line y equals x, you can almost, if I draw that dashed line, in order to flip that whole thing over, you'll end up with that piece that I have drawn there. And again, what that does is it flips my domain and range. So now my domain is negative 1 to 1. My range is 0 to pi. That range, again, is going to dictate what part of the unit circle I look at. So it's going to be from 0 to pi, which would be this part of the unit circle. So when I go do an inverse of cosine, I'm going to look at the values between 0 and pi, which would be the first and second quadrants. All right, again, 0 here, pi here. So then I can ask you a question like, what is capital C cosine inverse of 1/2? This is pi over 3. That's where cosine gets you 1/2 is at pi over 3. It's what angle causes cosine to be that value. All right, and I can do this for lots of different values. So just to give you another example, where is cosine negative root 3 over 2? And the answer is 5 pi over 6. Right. Again, part of why we have to limit this restriction is if I gave you the inverse and I did not give you that capital letter and give you that restriction, the problem would be it would happen at more than one value at the same time. And then the question will be, well, how do I know which one counts and which one doesn't? That's part of why we restrict this. All right. So here's how sine and cosine look. All right. What I'm going to do is I'm going to run through each other one here. I'm going to highlight the piece that matters, draw your inverse, and show you the part of the unit circle. All right. So as we keep going here, we go to tangent. For this one, if I highlight it, it's this middle piece here. That piece is perfect. It's 1-to-1. It passes vertical line test. It passes horizontal line test. All right. So when I talk about this one, all right, first of all, this is y equals tangent of x. The restricted domain here, because of the asymptotes, I have to use parentheses. So this is negative pi over 2 to positive pi over 2. But now I have parentheses there because they're undefined values. The range is technically all real numbers. It includes all negatives and all positives. When I go to do the inverse of this one, right, the two vertical asymptotes, when I do the inverse, are going to flip and they're going to become horizontal asymptotes. Right? Just like x's and y's flip for the ordered pairs, it happens for asymptotes as well. So instead of x equals negative pi over 2 and pi over 2, now it's y equals pi over 2 and negative pi over 2. Right? Just like the original graph is increasing, the inverse will also increase. So this is y equals capital T tangent inverse of x. This domain, because it inverts, is all real numbers. The range is negative pi over 2 to pi over 2. What that does is, again, when I go to look at the unit circle, this range of the inverse tells me where to look on the unit circle. It is everything from negative pi over 2, which again is down here, to pi over 2. But notice I put open circles there because you're never actually going to include them. They'll be undefined values. So it is also the first and fourth quadrants, just like sine. And again, we could do any number of examples here, but I could just ask you, hey, where is inverse tangent a value of 1? Again, that is asking you, hey, what angle causes the tangent value to be 1? The answer is pi over 4. All right, so what I'm going to do here is I'm just going to kind of show you the other ones. Hopefully, then some things will make sense. And then we'll talk about how to use all of these. All right, so when I go to the next page here, if you look at this first one, this, if you didn't recognize it, this one is cosecant. So this one is a little bit weird because if I would try to include this whole first circle that I just highlighted, or that first little parabola looking piece, all right, that would not pass horizontal line test. So I can't use the whole thing. I can use this piece and this piece because, again, I want it to be connected and around the origin. So those are the two pieces that I'm going to be able to include. So when I talk about domain here, this is negative pi over 2 with a bracket to 0, but there is an asymptote there. It's just hard to see, and you don't see it on this picture necessarily. And then union 0 to pi over 2, but pi over 2 does exist, so I can bracket that. And the range is also disconnected. This would be negative infinity to negative 1 and negative 1 to infinity. Or sorry, positive 1 to infinity. So I look at these ordered pairs over here. This was a point at pi over 2 comma 1. There's a point here at negative pi over 2 negative 1. So those ordered pairs will invert when I look at the inverse. So again, this is capital C cosecant inverse of x. All right, at negative pi over 2, negative 1 is now a point at negative 1, negative pi over 2. The point at pi over 2, 1 is now 1 pi over 2. So they look like they're basically in the same spots. All right, the vertical asymptote at 0 is now a horizontal asymptote at 0. I'm going to try to do that a little bit better. Now the shape of this one's going to look weird because, again, it would reflect over the line y equals x. And so that top piece is going to reflect that shape. And this one's going to reflect this way. And again, the domains and ranges are going to flip. So the domain of this one is negative infinity to negative 1, which is where this graph would stop, and 1 to infinity. And then the range would be negative pi over 2, where the bottom point is heading up to the asymptote at 0, and then 0 to pi over 2. Negative pi over 2 to pi over 2 without 0 included would be from here to here. So I would include all of these values. You could technically put an open circle there. If you don't, it's not the end of the world, only because you're going to get an undefined values there anyway, and we've seen those pop up with the regular unit circle questions. So if you don't remember that open circle, not the end of the world. Right? And again, I could do any one of these as an example, but inverse cosecant of, let's say, 2, right? That would be the same as also saying, hey, where is sine 1/2? Right? And that would be at somewhere, I believe that's pi over 6. Right? This is secant. For this one, if I look at which part I can highlight, right, that part would be here, but I couldn't do the other part of that little part of the parabola because, again, that would fail horizontal line test. So I'm going to include this piece right here. All right. So if I label that domain and range, that would be, the domain starts at 0 because there's a point here at 0, 1. So the domain is 0 to pi over 2, but I can't include that because there's an asymptote there. And pi over 2 to pi with a bracket because there's a point here, again at pi negative 1. The range, just like for cosecant, would be negative infinity to negative 1 and 1 to infinity. Again, I invert those points, so now there's going to be a point here at 1, 0, and a point at negative 1 comma pi. Again, weird looking graph here because there was an asymptote, a vertical asymptote at pi over 2, so there's a horizontal one. This one's going to curve this way. This one's going to curve that way. All right. So the domain of this one, again, just flip. The range, just flip. When I transfer that to the unit circle, again, that range, right, is going to tell you from 0 to pi, basically. The only difference is you're not going to include pi over 2, but it's this whole first and second quadrant. So here, if I ask inverse secant of 2, it'd be the same as saying, hey, where is cosine 1/2? This is going to be a pi over 3. And I realize I forgot to label my graph over here. All right. So for my last graph here, I have cotangent of x. This one's going to be very similar to tangent because I'm going to look at that continuous first piece here. Right? That piece is going to be everything that I need, right, that passes horizontal and vertical line tests. So my domain of this would be from 0 to pi. Notice I'm using parentheses because there is an asymptote on either side. My range is all real numbers. So when I go over here to the inverse, this is inverse cotangent again with that capital C. All right, I have a horizontal asymptote at 0 and a horizontal asymptote at pi, because again, the verticals become horizontals, just like I switch everything for inverses. There was a point here on the original graph at pi over 2, 0. Now there's a point at 0, pi over 2. The original graph was decreasing. This graph also decreasing. The domain of this is all real numbers. The range is only 0 to pi. And that 0 to pi tells me, hey, it's everything from 0 over here to pi over here. It's just I have the open circles there only because I know I'm not including either of those values. They're undefined. And again, if you want to do an example of an inverse here, this would be inverse cotangent of 1. Where is cotangent the value 1? That would be a pi over 4. All right, so what this lets me do is start to then say, okay, just start practicing, hey, figuring out our inverses. All right, I will post a couple of examples of that here. So ignore the next little graph that's there. All right, but then it just becomes a game of, all right, learning which ones. So if you kind of notice a pattern here as I scroll back up through them, all right, basically it breaks down into 2 categories. Am I looking at the first and fourth quadrants? But again, when I talk about the fourth quadrant, I'm talking negative pi over 2 and up. Or am I looking at the first and second quadrants? And you can basically see it breaks down into 3 of each. All right, so 3 of them, cotangent, secant, cosine, are all quadrants 1 and 2. The others are in quadrants 1 and 4. So that'll be a kind of a pattern that'll help you here. And then we just start to do examples of this. We say, hey, where is inverse sine of, not pi over anything, because remember we're looking for a trig value. Let's say, again, root 2 over 2 is one that pops into mind. Again, where is sine root 2 over 2? Again, I can only look for that one. If I scroll back up, from negative pi over 2 to pi over 2, it would be here. All right, that's at pi over 4. I realize I just did that example, but it was still worth it because I didn't have to go back to it. All right. Where is cosine root 3 over 2? All right. Again, I can look at quadrants 1 and 2 for that one, but it's positive, so I know it's in quadrant 1. Notice anytime I see a positive ratio, it's going to be a quadrant 1. And then it's a matter of where the negatives are. Is it in quadrant 2 or is it in quadrant 4? So for this one, this would be pi over 6. I'll do a tangent 1. Hey, where is it? Negative 1. All right, so I would need the sine and cosine values to match, just one have a negative. Again, for that one, if I look at the unit circle, and I won't scroll, you can look at your own notes. This is between negative pi over 2 and pi over 2, so this would be at negative pi over 4. Where is sine negative root 3 over 2? Inverse sine of negative 3 over 2. Again, you're looking at quadrants numbers 1 and 4. It's down in quadrant 4. Sine is positive root 3 over 2 at positive pi over 6. So this answer is going to be, oh, just kidding. No. There we go. Negative pi over 3. All right. So that's a couple of practice questions. All right. I'll write a couple more of these down. Let's see if you pause it, try a couple, see if they make sense. If they do, awesome. If they don't, we'll figure it out tomorrow or the next day whenever I see you again.